Hello class, this is a video tutorial on the introduction to differential equations. When solving equations, the solution is a single value that when we substitute makes the statement true. So we've seen how to solve equations such as these, and we know that if we take this value and substitute it back into the original equation, as shown here, we will get a statement that is true. So in this case, we get 17 equals 17. Likewise here, this quadratic equation, when we substitute, well, solve and then substitute, like so, we get a true statement, 0 equals 0. You can test substituting any other value just to really demonstrate this idea. Now, with that in mind, a differential equation are those that involve derivatives where the solution is an equation. In particular, it is an equation that is the original relation or function. Let's demonstrate here. So for this differential equation, so this is what they will look like. We are looking for a equation that when we differentiate, it will give this equation. So the solution to this, or this particular one, the solution to this one is this function. I'll demonstrate to you now that we can actually substitute this for y. Because y is equal to this function, we can substitute it here. It will look like this when we substitute it, so dy on dx. Notice how we substituted it for y, like so. Now this may look kind of strange because we normally write it like so, d on dx of this function, which if we differentiate it as normal, we get, so differentiating this, we get 4x cubed minus 7. Okay, so the same idea. You can pause and give this one a go yourself if you'd like, but I think you get the idea of how we can substitute values into a derivative expression. So that is the first key point that we are learning about differential equations. So we are looking for equations that when we differentiate gives us the original, or gives us the equation that we began with. The second point is that we learn and we view integration and differentiation as a mathematical operation that can be applied to both sides of an equation. So just as we could subtract both sides and divide both sides, we're now looking that because we're learning about differential equations, we treat integration and differentiation as another mathematical operation. As a result of this, calculus notation should now also be viewed as a manipulatable or another variable. Let's demonstrate here. So notice how we have dy dx. Normally we saw this just as notation. We can now treat, well, we should look at this now as another variable that we can multiply both sides by dx. It will give us the expression of dy equals 4x cubed minus 7 dx. This has now a 1 in front of it, and as I stated before, we can integrate both sides like so. When we integrate this, 1 dy gives us y is equal to, when we integrate this, this will give us x to the power of 4 minus 7x plus c. So the key takeaway from this is we can multiply and manipulate calculus notation, and we can treat integration has something we can do as an operation we can do to both sides of an equation. Likewise for this, y prime is just a placeholder for dy and dx. I'm going to move this across. So we get 4 minus 3x squared. We can multiply both sides by dx. Now remember, when we do this, we imagine it like so, where we have the dx for everything. And now we integrate both sides. This gives us y is equal to 4x minus x cubed plus c. Okay, so the second point is that we view integration and differentiation as a mathematical operation that can be applied to both sides of an equation. Third key point. This one's nice and quick. The order of a differential equation is the highest derivative found in the question. So in this case, we have the first derivative. So this is order 1. In this one, don't look at these because this is a function of x. Rather, we look at these ones. This is the second derivative. So this is order 2. Even if it's presented in a rather mixed up manner, we still have the first derivative here. So this is order 1. Likewise with this, even if the notation looks different, we still have the second derivative here, f double prime. So this is order 2. It is the highest derivative of this differential equation. In this case here, we have the third derivative, y triple prime. So this is order 3. In this one here, if you look carefully, there are no derivatives, so this is order 0. Okay, so the order of a differential equation is the highest derivative in the question. The fourth point, a differential equation is separable if all of the y variables and derivatives can be factored and isolated from all the x variables and derivatives. This one's a little bit trickier, so I'll just demonstrate here. So these two are separable and these are not. I'll demonstrate to you why. As shown before, we can multiply both sides by dx, which gives us this expression. Remember, it's treated like this. And now we can divide by y, which will give us 1 over y dy equals 3x over x squared minus 1 dx. Notice how all the y variables and derivatives are on one side, and all the x variables and derivatives are on the other side. Same deal for this one. We get dy on dx. I'm going to factor out y, and then multiply both sides by dx. So my right hand side becomes 2 minus x squared dx. And at the same time, I'm going to divide by y. I'm going to write it as 1 over y dy. Once again, notice how all the y variables and derivatives are on one side, and x variables and derivatives are on the other side. If you take a look now and compare these two, it's a very slight difference, but as I'll demonstrate now, we actually cannot separate this y variable from the x derivatives. So I'll demonstrate here. For this one, I'm going to subtract y first. So I get dy on dx minus y 3x x squared plus 1, minus 1. But now when I multiply by dx, remember how when we multiply every term in the expression. So this will give us dy minus y dx equals 3x on x squared minus 1 dx. Now, no matter what you try and do, these two can never be separated. Okay, so we could move this along here. If you try and factor out y, that's actually not possible because we have to treat dy as one variable. You cannot factor y from this. So this is not separable. Likewise for this one, I'll demonstrate again. If we try and notice how there's a slight difference, very slight difference. We just made this one y squared. So when we factor out y, we get 2y minus x squared. This becomes dy dx. If I divide by y, I will get 1 on y dy, and multiply by dx at the same time, we get 2y minus x squared dx. Notice how this still has a y variable. Now if you're thinking, oh, let's just move this to the left-hand side, we actually have to expand this first. It'll become 2y dx minus x squared dx. So even if we try and move this to the left-hand side, it will still become 1 on y dy minus 2y dx equals negative x squared dx. Notice how this y variable and x derivative cannot be separated. So separable and not separable. And lastly, a differential equation is considered to be linear if it is of the form f0x y plus or minus f1 of x y prime, f2 of x y double prime, all the way up to some function of x times any derivative of y. Now, this may look really funky, but these f and g, they are just any differentiable function. Y to the power of n, it's not really power, it's y to the nth derivative, are just derivatives of some function of y. So I'll demonstrate to you now. This is of the form, just these last two. It's 1 y prime, so 1 is a function of x, y prime, equals this g of x. If we move across, we get 5x cubed. This one here, once again as well, this is a, this are these ones, y prime is this one, equals 0. Okay, so notice how we just have regular derivatives of increasing or decreasing values. It doesn't matter what function they are multiplying by, they are still a linear differential equation. Okay, so notice how these have y prime, y, double prime, triple prime, single, and the functions that they are multiplied by are just functions that we can differentiate. So once again, take a look. Y, it's multiplied by a function that we can differentiate. Y prime, it's multiplied by a function that we can differentiate, equals 1. So we just took gx and moved it across. That is still a linear differential equation. Now, it may seem rather difficult to imagine, but a nonlinear differential equation is if you just take y prime and we square it, like so. So that is a non-linear differential equation. Likewise here, we have the second derivative, and we square it or raise it to some power. That is a non-linear differential equation. So in this topic, we'll be focused solely on separable linear differential equations of order 1 or 2. So in all summary, we need to learn and understand of these criteria for differential equations. Okay, so I hope that gave you an insight into the introduction to differential equations. Hope to see you in the next video, and best of luck.